Have you ever seen something that looks like pure magic? You're looking at a substance, it's totally clear 1 second, and then boom, it's dark brown the next. All you did was change the temperature. It's not a trick though, it's an amazing story about chemistry and balance. So, our whole story today kicks off with this one simple mystery. We've got this sealed flask of gas, you warm it up, it gets darker. You cool it down, it goes clear again. What is going on here? Why does it do that? All right, let's meet our chemical chameleon. Inside this flask is a mix of two different gases. On one side, we have dinitrogen tetroxide, which is totally colorless. On the other, nitrogen dioxide, which has that dark brown color. The wild part is that they're constantly turning into each other, back and forth. The color we see, it just tells us which gas is winning out at that particular moment. To really crack this color change mystery, we first have to understand this invisible dance that's happening inside the flask. And that dance has a name. It's called chemical equilibrium. Now, the most important word here is dynamic. You might hear equilibrium and think everything's just stopped, right? Frozen. But that's not it at all. It's a state of perfect, balanced action. Imagine for every one molecule of colorless gas turning brown, at that exact same moment, a brown one turns colorless. The reactions are always happening, but because they're in balance, the total amounts of each gas just stay the same. Here's a great way to think about it. A painting on a wall is in static equilibrium. It's finished, it's not changing. But now picture a really busy store. People are always coming in and other people are always leaving. It's a constant flow. But if 5 people walk in every minute and 5 people leave every minute, the total number of shoppers inside stays the same, right? That's dynamic equilibrium. And that's exactly what our gas molecules are doing. Okay, so we've got this balanced, dynamic system. But what happens when we mess with it, when we poke it? Well, that question leads us to a golden rule in chemistry that explains pretty much everything. And here it is. It's called Le Chatelier's principle. It's a bit of a mouthful, I know, but the idea behind it is incredibly powerful and honestly pretty simple. The key word to remember here is counteract. I like to think of it as a chemical system that has a bit of an attitude. If you try to heat it up, it'll do everything it can to cool itself down. If you try to squeeze it into a smaller space, it'll try to shrink and take up less room. No matter what you do to it, the system just pushes back to try and undo what you did. So how do we poke this system? Well, there are 3 main ways we can apply what chemists call a stress. We can change the amount of one of the chemicals, we can crank up the temperature, or we can change the pressure. And each of these is going to trigger that pushback response. All right, we've got our clues now. We know about dynamic equilibrium, and we know about this pushback principle. So, it's time. Let's put it all together and finally solve the mystery of our color-changing gas. Okay, let's look at our chameleon reaction one more time, but look really closely at the left side of the equation. See how heat is written there like it's one of the ingredients? That is the final crucial clue. It tells us that the reaction going to the right, the one that makes the brown gas, actually uses up heat. It absorbs it. And now it all just clicks into place. When we put the flask in hot water, we're adding heat. The system hates that. So it pushes back by doing the one thing it can to get rid of that extra heat. It shifts to the right, favoring the reaction that absorbs heat. The result? More of the dark brown gas. And the opposite is true too. We put it in ice water, we're sucking heat out. So the system pushes back by trying to make its own heat, shifting to the left and making more of the colorless gas. It's that simple. Now, pressure is a really interesting one. It's kind of a 2-step story. If you take the gas in a syringe and squeeze it, the first thing you see is the color gets way darker. That's just because you've squished all the molecules closer together. But then, Le Chatelier's principle kicks in. The system pushes back against that high pressure by shifting to the side with fewer gas particles. And in our case, that means taking 2 brown molecules and turning them into one colorless one. So after that first dark flash, the color actually starts to get lighter again as the system rebalances itself. Pretty cool, right? You know, this whole pushback idea isn't just a theory. You can literally see it happen in the data. So to see how this works with concentration, let's check out a different example. This graph is tracking the amounts of 3 different chemicals over time. You can see everything's nice and stable at first, then something happens, and the system has to scramble to find a new balance. All right, now it's your turn to be the chemist. Look really closely at the graph, right at that moment labeled time I. You see that sudden, sharp spike in one of the lines? Based on everything we've talked about, what do you think happened to the system at that exact moment? If you guessed that someone just dumped in a whole bunch of substance B, you absolutely nailed it. That's the sudden spike. And then look what happens immediately after. The system pushes back. The amount of A and B start to drop as they get used up, and the amount of the product, C, starts to rise. It's working to counteract that sudden flood of B, trying to get back to that happy, balanced state. So this is a really neat lab demonstration, but does it have anything to do with our actual lives? Well, it turns out that this pushback principle isn't just a curiosity. It's one of the most important concepts in the entire modern world. This right here is the Haber-Bosch process, and it is, without a doubt, one of the most important chemical reactions in all of human history. Why? Because this is how we make ammonia, and ammonia is the key ingredient in the synthetic fertilizers we use to grow a massive amount of the world's food. Seriously, without this one reaction, our planet couldn't support nearly as many people. So this is where engineers use Le Chatelier's principle like a powerful tool. Their goal is to make as much ammonia as possible, which means they need to force this reaction to the right. How do they do it? They apply crazy high pressure, which the system pushes back against by shifting to the side with fewer gas molecules, the ammonia side. They also constantly pull heat out of the system. The reaction naturally produces heat, so by removing it, they trick the system into making even more heat, and therefore more ammonia. So when you get right down to it, this isn't just theory. Understanding how to manipulate this invisible balance, how to push it and pull it exactly where you want it to go, that's directly responsible for our ability to make enough fertilizer to feed the planet. And that's really the biggest takeaway here. This simple principle, the one that explains why a gas changes color in a flask, it's the very same idea that allows us to produce enough food for billions of people all over the world. It's just an incredible link between a basic chemical concept and our everyday existence. It really makes you think, doesn't it? From the way our bodies regulate oxygen to the planet's climate system, our world is filled with these delicate, dynamic balancing acts. So the question is, what other invisible equilibriums are out there, quietly shaping everything around us?